Thank you everyone for coming. My name is Gabriel Gutting. I am the team lead for the Kodiak project. So this project is a joint effort with Kodiak Aircraft. They have sponsored our project. So Kodiak Aircraft is an aircraft manufacturer from Sandpoint, Idaho. They design and build the Kodiak 100 light utility aircraft. And they have tasked us with designing a project. So this is also in coordination with Rose-Hulman Institute of Technology out of Indiana. We have Dr. Mayhew and Dr. Singalkar, as well as a student, Eric Harbaugh from Rose-Hulman, working with us on this project. So let's look at the FAA project. So this is the problem statement as defined by Kodiak. They want us to design and build a system to do flammability testing for interior aircraft materials. So any of the materials that are inside of the cabin of the aircraft exposed to the
we weren't going to get through.
Did we lose audio?
I lost you.
I didn't mute it again for some reason. Can you hear me now?
Yes, thank you, Gabe.
There we go. Sorry about that. Hopefully that stays on. So our problem statement. Kodiak has provided us a problem statement to design a flammability testing cabin. So this is testing the flammability of materials used on the interior of an aircraft cabin. So there are a variety of regulations and fixture positions that need to be tested, adhering to the FAA guidelines. So to accomplish this, we split our team up into 4 subgroups. We had a great group working on the structure of the cabinet body, a group working on the gas burner system, and a group working on the fixtures to hold the material. So these are some pictures of some of the industry standards that we were working with. We are looking at building a cabinet to contain this test in a draft-free, steady conditions environment. We need to hold materials up to a Bunsen burner flame and test how far the burn travels in a specific period of time. So that is the baselines of what our testing projects look like. We need to build the system to be able to do these tests. So now we will have Tom talk about the cabinet and smoke evacuation systems.
All right, thank you, Gabe. Good evening, everyone. My name is Tom Piazza. I was a part of the cabinet subgroup team along with my team member, Robert Romeo, and I'm going to be talking to you about our cabinet design. So the big thing when we were doing this project is we need to make sure that our cabinet was FAA approvable. The FAA gives us a set of guidelines and technical specifications that we need to meet in order for our cabinet to be certified to produce accurate experiment testing. Now, some of these guidelines include draft-free, so the Bunsen burner flame needs to be a steady burn. We also need a corrosion-resistant bottom. There is dripping flammable material from the cabinet that can possibly fall onto the floor, so the FAA requires that we have a corrosion-resistant bottom. However, we made the whole cabinet corrosion resistant with stainless steel, as I'll get into in a little bit. We also have dimensional requirements that we need to meet. The cabinet dimensions that the FAA states we need are 24 inches long by 12 inches deep by 31 inches high, plus or minus 1 inch on each tolerance so that we can have just a little bit of wiggle room, but we still need to fall within those dimensions. The other guidelines that we specifically need to meet are for the 4 different types of tests that our cabinet can produce. We can do the horizontal burn test, the vertical burn test, the 45-degree burn test, and also the 60-degree wire test. Now, it's important to note that some cabinets on the market can be purchased specifically for one type of test, but our cabinet, because it encompasses all these tests in one cabinet, needs to be able to abide by every guideline that the FAA states for each of those specific tests. So it's very important that we follow the FAA guidelines throughout this when creating the cabinet. Now, we're only creating this cabinet one time, so we wanted to keep the cost low. We don't have the luxury of having mass-produced parts like some commercial companies to build the cabinet where they can just order their parts and simply put it together. So we're looking for ways which we could cut down on costs, such as manufacturing ways and different materials, while still keeping a high-quality cabinet. And we did that with our design. And the reasons we chose this design, firstly, was for ease of assembly. So if you look at the pictures to the right, you can see the bigger piece is our left, back, and right piece. That is the structural piece for our cabinet, which is going to keep everything sturdy when it's all put together. The piece above that is the top piece. Now, the top piece and the bottom piece are exactly the same. The only difference is the top piece has the exhaust holes drilled into it, while the bottom piece has 4 holes, a hole in each corner for the stand mounts. Now, when we're putting this together, we take the top and the bottom piece and we weld the bends of those pieces to the edges of the left, back, and right piece. What this does for us is it creates a single piece of metal by fusing the metals together through welding, It also meets a requirement because it becomes a draft-free cabinet because no air is going to be able to get in through those seams. While doing this, we also keep the manufacturing costs low by using the bent stainless steel sheet metal at 16 gauge thickness, which we use to bend to make these parts. Also, because of the welding, we also significantly increase our structural integrity of the cabinet because now all the pieces, instead of 3 pieces, it's one single piece. We also built an exhaust system for the cabinet. Now the exhaust system is an integrated hood, so if need be, it can be removed. What you would see if it is removed is the picture on the left with just the baffle. That can work, but if more hazardous materials are being burned, they might want to put on the exhaust hood so they can evacuate the hazardous smoke. And that is evacuated by a 4-inch exhaust ducting inline with an exhauster fan. Now I'm going to pass it off to my team member, Robert Romeo, to talk about the different analyses we performed on the cabinet and also our door design.
Thank you, Tom. I'm Robert Romeo. I also work with Tom on the cabinet subsystem. So our heat transfer analysis was used to determine the thermal capabilities of our cabinet. What designed our cabinet was 2 major analyses, thermal stability and structural stability. So through heat transfer analysis and thermodynamic analysis, we determined that our cabinet would be a safe temperature at the exterior surface through operation. And to do this, first we used thermodynamics to determine the distribution of the highest temperature we could anticipate on the interior of the cabinet. We've got a flame at a given temperature for a given amount of time, and using that information, we determine what the temperature of the air could possibly be. Then we use a heat transfer analysis at a stable platform, stable rate, to determine how the heat propagates through the cabinet. Doing that, we used a heat resistor network. The simplified one is presented here. The more complicated one we simplified down by removing the insignificant components. Here you see the interior maximum temperature of the cabinet through to the exterior surface of the cabinet. And using this information and the resistances of our different materials, we determined the minimum acceptable material thickness at the exterior dimensions of our cabinet. And that's what led our design in determining what our minimum was from a thermal standpoint. And then we also needed to determine from a structural standpoint what our material minimums were. So towards determining our structural stability, we used an FAA analysis. FAA is finite elemental analysis, and to do this we use the material properties, the geometry, and the external loads to determine the internal stresses resultant in our cabinet. So we developed an initial model early on in our design process to get a rough idea of what the most significant loads on our cabinet would be when it comes to resultant stresses. The structural loads and environmental loads are loads that we anticipate would be the most significant in our cabinet. The structural loads are loads that are static, resulting from components of the cabinet itself. The material holder fixtures on the inside and the weights that they present, the electrical box on the side, everything that adds weight to our cabinet. In addition to that, our environmental loads are dynamic loads that we can anticipate would be present from environmental factors, mainly the technician that would be working with the cabinet. So if they would go to side squeeze to lift the cabinet up, or lean on the cabinet, say on a corner or any other surface in order to peer inside, we anticipate what that load would be, give it a factor of safety, and then determine what the initial stresses were. So we use our initial model, determine what the most significant loads are, and then later in our design phase, we create our final model. This model present here exactly replicates what our design cabinet was through the sheet metal and welding process. Now, no design is perfect. That's where the engineering comes in with FAA. But we were able to use this tool to analyze our most significant loads and determine what our anticipated stresses resultant were. And it turns out the most significant load was from our 60-degree wire test hanging on the top ceiling of our cabinet in the middle, and it has an 11-pound weight on a pulley system on a sheet metal surface. This resulted in approximately 6,200 psi stress, and when you compare that against the yield and the failure stress, the yield stress being 30,000 psi, we have a factor of safety of about 4. So through both of those analyses, we're pretty confident that our cabinet's going to be thermally and structurally sound. And those are elements that went towards our design that Tom presented earlier. Now, another thing our cabinet subsystem worked on was the door design. So the door is another significant part of our cabinet, and the most significant part of that door is the window component. The technician during the project, during the operation of the cabinet, will be peering inside to determine many factors during the burn process. They'll be looking at burn length, burn time, dripping flammable materials. They need great vision to see everything that's going on in there. So we provide a large glass window for them to view through, and that presents design challenges. And around what glass we chose were a few significant elements. We needed a high thermal shock resistance, owing to the temperature of the flame inside of the cabinet and the differential created. We needed high structural stability, and we wanted something safe. And so that's how we landed on tempered glass. Tempered glass has high thermal shock resistance. It's structurally sound. It's used in automotive glass as well, so that can give you an idea of the order of strength it has. And it's also safe. It breaks into small pieces instead of shards, so if it would fail during the operation of the cabinet, our technician would be safe during that failure. The door also involved a stainless steel construction pairing the cabinet body, anti-corrosive properties, structural stability, and aesthetically similar. It has a stainless steel frame, stainless steel piano hinge, and most of the fasteners are stainless steel as well. Now it also has that draft-free condition that's important to the overall condition of the cabinet. And we achieve that through the piano hinge that eliminates gaps in the hinge, as well as through a combination of a cam latch and a high temperature rubber seal system. The cam latch draws the door in closer as it closes, and the rubber seal is compressed to eliminate airflow between the door and the cabinet body. And now I'll transition over to Gabe to explain another subsystem.
Thank you, Robert. My name is Gabriel Gunning, and I worked with Eric Harbaugh from Rose Holman with the design of the gas burner and movement systems. So when starting this, we had to look at the technical specifications for the burner. Again, the FAA is very strict with the specifications that we need to meet. So we looked at first the flame temperature limits. We know we need a flame that can reach between 1500 and 1700 degrees Fahrenheit. We also know that we need a flame height limit of 1.5 inches, and that the gas can be propane or methane at a specified pressure. So that was our fuel requirements. We also had requirements for the burner itself. The FAA asked that the burner can move inside the cabinet with the operator standing outside so that there's no drafts. This is so that we can move the burner to one side of the cabinet, light it, and adjust the flame, and then move it into position. That way we have our burner set, our material set, the door closed, then move it into position to accurately start our timer, expose it to the flame for a certain amount of time, and bring the burner back. So we know the burner must move inside of the cabinet. And we also know we need a manual shutoff and backup system in case there is an overburn or other failure. We need to be able to shut the flame off quickly. Looking at these technical specifications, we first designed a gas supply system. We chose to go with propane because of its wide availability and portability. Kodiak does not currently have the capabilities to do methane, so we decided propane would be the most cost-effective solution. We also opted to go for a 1 pound or 20 pound bottle depending on how much testing you're planning on doing. We can run it off of a small barbecue size or a camping size cylinder or a barbecue size larger cylinder if necessary. This design also features an adjustable pressure regulator that can go between 0 and 5 psi, so we can hit that required 2.5 as necessary. This system uses a manual shutoff valve, very obvious red lever that you can shut off if you need to. It is located on the high pressure side of the system, so the low pressure side will quickly evacuate and your flame will quickly die off. We also use a fine-tuned needle valve on the control panel on the low pressure side of the regulator so that you can fine-tune the adjustments of the fuel as it goes to the burner to reach your specified burner requirements. Now for the burner movement. We know the burner must move inside the cabinet, and there are ways to do this mechanically or automated, and we decided to try and make an automated system with a backup mechanical system. This system must have the function of executing timed tests and move the stage one dimension inside the cabinet back and forth. So Eric at Rose Holman designed this system, and he used a ball screw linear actuator system to have a carriage on it that will move the burner back and forth. He is controlling that with Arduino microprocessor and a stepper motor and limit switch system. The Arduino and stepper motor can move the ball screw back and forth, and the limit switch tells it when it is at the home position so it knows where it's at in the travel back and forth. To interact with this system, we have integrated an LCD display and a toggle switch system to be able to select your testing. You can flip the toggle switch, the LCD screen will say what test you have selected. It will move the burner or start a digital timer to count off how many seconds have passed. Then it can move the burner back to its original position. This user interface is controlled on a panel on the side of the control box. This control box features the LCD screen at the top of the control box with a row of toggle switches below. So these toggle switches will be able to control your testing as well as a reset button to move the burner back to its home position. And right in the middle of the control panel is a very obvious red kill switch. This will shut off all power to the system if there is a failure in the electronics. Located above the control panel is a switch for the exhauster fan. This switch will be able to be wired into an inline exhaust fan on the exhaust hood to turn on the exhaust after the test so you can evacuate the smoke before you open the cabinet. Located at the bottom of the control panel is the needle valve for the fuel system in an easy to reach location so you can adjust the fine-tuning of the fuel lines. And next, Sally will be talking about the material holders.
Thanks, Gabe. I'm Sally Stainby, and I worked with my teammate Jacob Dahl on the material holders. So, what function do the material holders serve? Well, our sponsor tasked us with creating a multifunctional cabinet that would be able to accomplish 4 different material tests. Because each time Kodiak wants to replace or modify a material, that material has to go through rigorous testing to be certified by the FAA. So with this cabinet, Kodiak is now able to do that independently, all 4 tests, without sending it to a third party. So these 4 tests are the wire test, mounted at 60 degrees, and the vertical, horizontal, and 45-degree tests for materials such as fabrics or insulation. So the ultimate goal of the material holders for each test is to accurately secure the sample of specified dimension over the burner at a distance determined by the FAA. But we also wanted to make a design that was easy to manufacture and easy to use and affordable. So out of the 4 tests, the 60-degree wire test was definitely the most complex, had the most complex requirements that we had to accommodate. I'll try to summarize it to its setup to give you an idea of its complexity. So we needed to have 24 inches of exposed wire orientated at 60 degrees, one end clamped at the base of the cabinet, the other end wrapped around a pulley, and then pulled down by a weight. Then the burner had to be orientated perpendicular to the wire at exactly 8 inches up along the length of the wire, with a 1-inch gap remaining between the barrel of the Bunsen burner and the wire. So needless to say, Jacob and I got a lot of trigonometry in during this project. So our final design consists of permanent mounts drilled into the base of the cabinet, the sides, and the ceiling. And the appropriate frames can be inserted and removed from those mounts. This layout was affordable and easy to manufacture, as the mounts and frames all came from the same sheet of stainless steel. And then the rest of the process, the grinding, the bending, and the welding was done here on campus in our machine shop. So our design optimizes several important functional features. The permanent mounts ensure accurate and precise positioning between each sample and test, and provide more durability and stability than even the FAA's original handbook models. The flat frames conserve storage space, and the material holders are simple and easy to use. Basically, you just need to clamp your material between the frames, mount it on the appropriate mount, and then close the cabinet, flip a switch, and the burner will go to its pre-programmed position for that test, and you're ready to run a test. So now I'll hand it over to Jacob, who's going to put the pieces together for us.
Thank you, Sally. As previously stated, my name is Jacob Dahl, and I'm another member of the Material Holders Subteam. This is two pictures of the orientations of the vertical test and the 60-degree wire test, as they'll be situated in the cabinet when they are needed. As we've shown throughout the presentation, our testing cabinet accomplishes the primary requirements for FAA approvability. A key feature that the current cabinet has incorporated is an automated burner movement system for accurate and quick positioning of the burner for each individual test. The design also has the capability to perform 45-degree, 60-degree wire, vertical and horizontal tests within a single cabinet enclosure. Due to the absence of a smoke hood in the Kodiak laboratory facility, a smoke evacuation system has been designed that integrates with the top of the cabinet. The flammability testing cabinet necessitates the usage of a high-temperature flame and flammable gases, which raised several safety concerns we had to address during the design process. To reduce the risk of an out-of-control flame, a manual gas shutoff valve was placed in the gas supply system to quickly shut off gas to the burner in the event of an out-of-control burn. Additionally, a power shutoff switch was integrated into the control panel, allowing the operator the ability to turn off the electrical supply to the entire cabinet, again, choking out the flame. If the automated movement system suffers a malfunction while a test was being conducted, a manual movement system was incorporated into the design so that the operator could move the burner away from the burning material to a safe location. Our smoke evacuation system will be capable of removing any hazardous fumes a sample might release during testing from the cabinet before the operator has a chance to inhale them. Although our primary objectives were completed, there are still a few loose ends associated with the project. Initially, Kodiak provided the team with a stretch goal to provided extra time to write a user and troubleshooting manual, but unfortunately the team did not have the time to provide these manuals. The automated system is tested and assembled, with some additional fine-tuning for the timing limits for each burn test would further improve the system. Additionally, a thermocouple could be integrated into the system for further operator convenience. Due to the specificity of the 60-degree wire test requirement, the wire clamp lock and the angled mount for the burner were not yet manufactured. We had wanted to wait until the 60-degree wire test was mounted in the cabinet so accurate measurements could be taken for the dimensions of these two systems. Finally, we had wanted to provide some side baffles to the cabinet to further limit the draft entering the cabinet and incorporate a system to eliminate all the air entering the cabinet so the exhaust fan could choke the flame, again for further safety procedures. Kodiak provided the team with a budget of $5,000 to build the cabinet. The most expensive item of our manufacturing was the cabinet material and production. The cabinet sub-team utilized a local manufacturer to obtain and construct the cabinet, who charged them far less than their initial budget estimate. Each sub-team made reducing the cost of their components of the project a priority, and thus our final cost ended up being only $1,900. The entire team would like to thank our advisors, the Kodiak contact personnel, and Eric Rose Holman, who's attending currently online. Thank you for listening. Any questions?
Wow, thank you guys very much. That was excellent. I really, really appreciate all the hard work you guys have put into this. The presentation, as you went through it, you answered all the questions that I was coming up with along the way. I love how you organized it and had all the pictures. Very well done. I can't thank you enough.
Thank you, Sarah. Any other questions, comments? Thank you for attending.